Welcome everyone to section number 6. We are tackling surface area this time around. And actually we're going back technically in this video. We're going to be talking about the chapter 15 version of surface area. This is actually brought up, we skipped over it, and now we're coming back because kind of the two fit together very nicely here in this section. And so our main objective is, right, we're going to define and calculate surface area over explicit surfaces. Right, I'll remind you of what those are here in just a second, but the claim is that just as arc length is an application for a single integral, surface area is going to be an application of double integrals. Right, so this is an application of double integrals here. And so yeah, as the title suggests, we're only going to use the 15.6 version of surface area, that is surface area over explicit surfaces. Explicit surfaces look like z as a function of x's and y's. So z is a function of x's and y's, and we're going to be calculating out surface area in this case. Okay, so here's the theorem. Here's what we're going to be using. All right, the area of the surface of this nice explicit surface, z equals a function of x's and y's. And of course, we should have our partial derivatives be nice and continuous. Well, this surface area, so the area of the surface S, is going to be equal to the double integral over that region D in the xy plane, right? So D is made up of x and y values. All right, times, let's see, the square root, and it's going to be f sub x squared plus f sub y squared plus 1. And this should kind of look like our old arc length equation from back, maybe even in Calc 2 we brought up something like this. And so the claim is, yeah, we've seen arc length quite a few times, but the original equation that we were given, right, for kind of an explicit surface, right, y equals a function of x, was this right here, right? Arc length was equal to, again, the integral from a to b of the square root of a derivative squared plus 1, right? And so this looks very similar to the equation that we now have, but now we have partial derivatives, right, because it depends on x's and y's. So you take the partial derivative of x, you square it, the partial derivative of y, and square it, plus 1. And right, you should say, okay, maybe why is it this way? In fact, I forgot, here's my dA. But you could ask, why is this equation the way it is, right? Why is this the right thing to integrate, right? And anytime you have a theorem, right, there is indeed a proof. Unfortunately, I'm not going to show it to you here. We're actually going to prove, or give you the idea of kind of a stronger proof for our parametric surfaces. So that's coming up here in a little bit. But for right now, I just want to explain how to use this. Okay, so assume that this is the right equation. Let's go ahead and calculate out the surface area of the part of this surface. So z equals a function of x's and y's over the triangular region in the xy plane with vertices 0, 0, 1, 0, and 1, 1. And so actually before this video, I went ahead and I graphed this for us. And so if we go over to our Monroe 3D Calc plotter, here is our equation, right? Z equals x squared plus 2y, and I can spin it around and we can see that it's kind of like, it's almost like a curved plane or something like this. It kind of looks planar and almost parabolic, right? Which that kind of makes sense because of the x squared and plus the 2y, so yeah, fair enough. Now we would like to calculate, of course, like this surface goes on forever. We want to calculate out the surface area of only a very specific piece of it. So I went ahead and I graphed a little bit more. So this right here is that triangular region, right? So that triangular region in the xy plane, 0, 0, 1, 0, 1, 1, right? And so we want to calculate out the surface area just of this piece of the surface, right? You can kind of see it. I made this a little bit transparent so that you could see the surface, right, kind of behind here. In fact, I can take this other one away. So we want to calculate the surface area of this yellow bit right here, right? So that is the surface area that we are calculating out. Okay, so let's get to it now that we kind of visualize what we're doing here. So I'm going to go ahead and calculate out the components. So maybe our f sub x, that's going to be 2x. Our f sub y, that's just going to be 2 in this case. And so I'm going to be integrating, so the area of my surface is equal to the double integral over my region. I guess they're calling it t in this case. This can be d or whatever notation you give, of the square root of f sub x squared, so that's going to be 4x squared, plus f sub y squared, that's going to be, let's see, 4 plus 1 times dA. Okay, so we could of course simplify this down. 4 plus 1 is just going to be equal to 5. And now we have to decide, how do I want to integrate this thing? And okay, well, we're going to choose this based on the region we're integrating over. So I'm going to go ahead and draw this region T in the XY plane here. So maybe I'll do it over here. So we have the vertices 0, 0, 1, 0, and 1, 1. So if I connect these, this makes the triangular region that I'm integrating over. And in fact, let's go ahead and shade it in as well. So this is this triangular region T that I'm integrating over. And now based on this picture, I would say, well, I probably don't want to integrate in polar. I guess you could, but probably not, right? So I'm going to go ahead and try to integrate with respect to y first, right? So let's go ahead and integrate this thing 4x squared plus 5, and I'm going to integrate with respect to y first and then with respect to x. So imagine I'm traveling in this y direction, moving upward. The first thing, the way that I enter into this region is through this nice horizontal line that has the equation y equals 0, and then I exit through this slanted one, right? And this contains the point 0, 0, and 1, 1, right? So this has slope 1 and intercept 0. This is going to be the line y equals x. So the y value here is x. And then I need to, let's see, kind of smash this down into one dimensions, or right, we could think, what are the x variables or x values that I need? It looks like from 0 to 1. From 0 to 1. Okay, so let's go ahead and evaluate this. Notice that there are no y's, so this is going to be the integral from 0 to 1, and when I integrate really constant with respect to y, this is going to be y times this thing, 4x squared plus 5. Evaluate that from 0 to x. And so I'm going to have the integral from 0 to 1 of, let's see, x minus 0, right? I'm plugging in x for y, then I plug in 0 for y, so this is just going to be x root 4x squared plus 5 dx. And that actually, that x kind of saves me. Otherwise, this would be quite a difficult integral to evaluate. But this x makes it very nice. So I'm going to go ahead and do a u substitution. U is equal to 4x squared plus 5, which means du is going to be 8x dx. And so I'm going to go ahead and rewrite this. X dx is equal to a du over 8. So I notice that I have an x dx that I can trade in. And the trade is x dx for du over 8. So that's the trade that I'm going to be making here. So this is going to be the integral. This is root u, right? Because u, again, was 4x squared plus 5. And then everywhere I see that x dx, right, I'm going to go ahead and substitute du over 8. And now the last thing, right, I'm going to go ahead and transform these into u values, right? Right now they're x values. I'd like to transform them into u values. So I'm going to use my equation right here, right? When x was equal to 0, that's my first x value down here. When x is equal to 0, we get out the u value. So x equals 0 implies that u is equal to, okay, 0 squared times 4. That's going to be 0 plus 5. So that's going to be u equals 5. Okay. And then the other x value is 1. So when x equals 1, this implies that u is equal to, let's see, 1 squared times 4, that's going to be 4, plus 5 is going to be 9. So that's going to be 9 here. Okay, so now let's go ahead and evaluate out this integral. This 1/8 is kind of along for the ride. This is really u to the 1/2 power, right? So we raise that up by 1. Then we multiply by the reciprocal of our new exponent, right? And go ahead, take the derivative of this, see that you get back to where you started. And now I want to evaluate this from 5 to 9, right? These are now u values. All right, so there's a little bit of cancellation here, right? 1/8 times 2/3, that's going to be, let's see, 4 here, so 1/12. And then when I plug in 9, well, okay, I'm going to have 9 to the 3/2 power. So 9 to the 1/2 power would be equal to 3. And then if I cube that, I'm going to get 27. That's pretty nice. The other one's not so nice, right? So there's no nice square root of 5. So unfortunately, this one is just 5 raised to the 3/2, and that's as good as we can answer, right? Now the big thing here is that if you were to double check this a little bit, you should get out a positive answer, right? If this is not positive, that's rather alarming. So in this case, yes, it is positive, but that's just like, right, a nice quick eyeball check that you can do in order to see if your answer's reasonable. Okay, that's one question down. Let's go ahead and try one more here. I recommend pausing the video, trying to get as far as you can in this one, and then I'll go ahead and spoil the surprise. Try this one on your own. Find the area of the part of the paraboloid that lies under the plane z equals 9. So again, try this one on your own, and then I'll give you the solution. Alright, so I don't have the solution all the way done out, but I want to start talking about some things with you. So first of all, find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So it's part of this paraboloid, but it stops here at a height of z equals 9. If you'd like to, right, you can go ahead and do Monroe 3D Calc Plotter. I went ahead and graphed it out here, just so we can really visualize it and not rely on my cruddy drawings. Right, so that's what it looks like there, and we want to know the surface of this paraboloid. Not the surface of the plane at all, but we want the surface of the paraboloid. That's what we're trying to find the surface area of. Again, you see our surface is given to us as z equals a function of x's and y's. And so when we go ahead and we start setting up this evaluation, right, I'm going to calculate out an f sub x and an f sub y. That's going to be 2x. That's going to be 2y. And so we're going to be integrating over some region here the square root of, let's see, 2x squared. That's going to be 4x squared. Once we did, right, it's 2x, the quantity squared. And then 2y, the quantity squared, will be 4y squared plus 1 dA. And then you have to wonder, okay, where are we integrating over, right? What is this region? And so you have to kind of sketch this paraboloid and the region that it lies over, right, in the xy plane. And so it looks pretty darn circular to me, right? And I got to wonder, okay, well, what is the radius of the circle? Kind of when do we stop, right? And well, kind of the radius of the circle, it depends on where this paraboloid here hits the plane, right? It's kind of like this piece right here that's being almost projected down into the xy plane, right down here. Okay, so let's go ahead and figure out what this is. Well, this is where the surface, x squared plus y squared, that's our z, is equal to 9. So this is a circle with radius 3. All right, and now based on that region, it really shows us that we should be integrating this with respect to polar coordinates. All right, so I'm going to go ahead and set up a polar integral here. I'm going to go ahead and write 4r squared plus 1 r dr d theta. And this is the circle of radius 3, so we're going to integrate from 0 to 3, and then our thetas range from 0 to 2 pi, since it's the entire circle. Now I'm going to go quickly through this integral, since again the hard part's really the setup here. Notice that there are really no thetas in any of this, so when I integrate really 1 d theta, that's going to give me theta. As I range from 0 to 2 pi, this is going to give me 2 pi. When I integrate this r integral here, right, I think we're going to go ahead and get 1/12 times 4r squared plus 1 raised to the 3/2. Go ahead, double check for me. If you take the derivative of this, do you get back to where you started? I hope the answer is yes. It is. Evaluate that from 0 to 3. Again, this is me going kind of quickly through the u substitution bit right there. And so let's see, the 2 pi and the 1/12, this is just going to make pi over 6. And now when I go ahead and I plug in 3, for instance, this is going to be 3 squared, that's 9, times 4, that's 36, plus 1, that's going to be 37, raised to the 3/2. And when I plug in 0, I don't just get out 0, right? When I plug in 0, I get 0 plus 1 raised to the 3/2. So this is going to be minus 1 raised to the 3/2, which is just 1. And so this right here, this is the area of our surface. The area of the part of the paraboloid that lies under the plane z equals 9. All right, that's it for the example, but however, I have one more section that I want to tell you about before class time. I've kind of alluded to several times that we've been talking about explicit surfaces, but we're going to have these things parametric surfaces, and we're going to calculate out surface area over parametric surfaces. So I want to give you a little bit of an introduction now before class, and then we're really going to use this a bunch in class. So I'm going to give you a nice, easy example here, but let's talk about things for a second. So first of all, if you have, a nice space curve, think about, we have a one-dimensional time, and we're going to 3 dimensions, right? So the space curve, right, is in space, right? So it looks something like this, right? It inputs t values and it outputs an x value, a y value, and a z value. Now, if you want to go from 2 dimensions, right? So I don't want just a curve anymore, or a squiggly line, but I actually want a surface. And so you may want a second dimension. right? But still this surface, it's embedded in space in 3 dimensions, just like the curve was embedded in space, 3 dimensions. So I want to take 2 dimensions, right, like lengths and widths, right, and I want to put this in space, right? And so it's going to look something like, and really you just sprinkle in one more parameter, right? So instead of just t's, we're going to have one more dimension, one more variable, one more parameter, whatever you want to call it here. So we're going to have s's and t's, right? So s's and t's, and so it's still we're going to have 3 components, one for each dimension, an x component, a y component, a z component. But this is how we're going to, actually parameterize surfaces. Okay, in the book, right, they have this habit of making things a little bit less clear, right? They like f's, g's, and h's instead of x, y's, and z's, but still this is the x component, the y component, the z component. They just want to call it something different. That's fine. And instead of t's and s's, they like u's and v's. Fine. So we'll get used to both of these things, right? So that way, if you see either or, right, you'll be able to recognize this as some parameterized surface. Okay, so this is what parameterization looks like of surfaces. Let's go ahead and actually parameterize one, right? So here's a nice surface. X plus y plus z equals 2, right? It's a plane that's hovering in space, and I would like to be able to parameterize it, but not the entire plane. I want to parameterize only the bit that lies above this nice, I guess, square in this case, but any old rectangle. So x is ranging between -1 and 1, and y is ranging between -1 and 1. And so again, this is really kind of the easiest scenario. It's similar to how we parameterized curves, but of course more complicated. But in this case, because you see x has well-defined bounds and y has well-defined bounds, just like when we were parameterizing curves, you'd say, well, what if maybe t was equal to x? And then t would range between -1 and 1. And what if, instead of y, what if we used s's? What if s was equal to y? And then s would range between -1 and 1. Because again, y ranges between -1 and 1. And so again, I want a parameterization. I want x's that depend on s and t. I want y's that depend on s and t. And I want z's that depend on s and t. So I have a parameterization with s's and t's instead of x's and y's. That's fine. And so everywhere I see an x, I'm going to write a t. And everywhere I see a y, I'm going to write an s. And then here comes the more difficult part. I need to get the surface, right? So I need to somehow get a z equation. Well, luckily I have z's over here, right? So I could go ahead and substitute in. Again, maybe everywhere I see an x, I'm going to put a t. And everywhere I see a y, I'm going to put an s. Plus z is equal to 2. And this is going to give me z is equal to 2 minus t minus s. And here is a parameterization of z that depends on s's and t's. So this is going to be 2 minus t minus s. And this right here is a parameterization for this surface. And let's go ahead and mention again that t should range between -1 and 1. And s should range between -1 and 1. Okay, so the last thing I want to do before we end this video is that the Monroe 3D Calc Plotter has a way to do parameterized surfaces. So let's go ahead and take a look at this. Wake up. There we go. So if we go ahead and add to graph, right, we're going to do a parametric surface right here. Now we have lots of options. They like x of uv, y of uv, z of uv. Fine, right? So instead of maybe t, I'm going to use v. Instead of maybe s, I'm going to use u. All right, and then z would be 2 minus u minus v, and we hit enter, and it's too much, right? We need to set the parameters for u's and for v's. So in this case, it's from -1 to 1, and from -1 to 1, hit enter here, and now we see that we get the same picture really that we had in my static sad drawing, but we get it here graphed in 3 dimensions. Alright, so this is a good indication that we're on the right track. Of course, these things get much more difficult, and that's what class time is going to be used for. I'll see you then.